Yeah. So I'm going to talk about rapid and robust visual navigation through active learning in ants. So it's basically um, pretty much what we were talking about. Well, what I was talking about within the discussion. So I just to call out that I'm going to start off. Namho, who's online from the US, will finish off, and a lot of the slides have been done by Amani, who was in the panel session and will be speaking a bit later. So this is the kind of outlook I take. So this fine gentleman here is J.J. Gibson, who was a philosopher, psychologist, and among some of the many wise things he said perception is about how sensory systems put information at the service of behavior. And what I take from this is the point that I was trying to raise is that basically, intelligence or intelligent behavior, adaptive behavior, if you prefer, is not a passive process. It's an active process. Animals actively engage with the environment, and particularly they're engaging with an environment that they've evolved in for a task that they've evolved for. So their brains, their bodies, the neural structures, their senses and behaviors have evolved for this particular task. We see that most obviously in insects, where the task that they're doing might be very specific. And so in ants and bees that I study, and in their visual navigation, so these are task specialists. They've evolved for this single behavior. And so evolution has had the chance over millions and millions of years to hone all of these elements for this one task. And so it allows us a lens in which to look at the particular questions that we're asking, right? How far can we push behavior to enable rapid learning? So in particular, what I'm going to talk about is how there's some visual scans, which are basically an active search, and they outsource the active search to the body. And I think it's one of the things that was similar to what we were saying in the discussion with you could do this scanning process in the head, but instead the ants seem to do it by their physical behavior, but they could do it in the head. And it's just one of these things where if we were going to emulate this, which when we do on robots, we tend to do this rotation in silica rather than in the body. But I think the principles, as Mike Milford was saying, the principles that we've observed do carry across to robots, but maybe not in exactly the same way. So I'm going to talk about the scanning. I'm also going to talk about these particular other behaviors, path integration and learning walks, if I've got time, which we can see will shape the incoming information to make it easier to learn and to use on the return. And I think in this particular example, it's quite easy to see how the behavior is making the world easier to learn. Okay, so a little bit of background. So the Hymenoptera, which is bees, ants, and wasps, are foraging specialists. And as I said, it means that their brains have been optimized by evolution for learning and navigation. So here's an ant brain. This is the ant environment in near Alice Springs in Australia. And here we've got an Australian desert ant. So we study ants that are in hot environments, primarily because pheromones have evaporated. So we know that in these environments, the ants are navigating using visual information, and they're individual learners. I'm sure Mike number 2 has talked a lot about this already, about how wonderful they are. But basically for us, they learn very, very quickly. There's a lot of evolutionary pressure because it's so hot to learn very quickly. And as I said, because it's so hot, we don't have pheromones. We know it's visual. But despite the differences, they've got the same toolkit as us to learn. They can work by odometry and visual learning, right? This combination of these two behaviors, same as us, same as all animals. The kicker here is they've only got 500,000 neurons, and their eyes are pretty low resolution. So we can model what they're doing. We could plausibly model the whole brain. We're not quite there, but we can be able to get close to it. but we know they can't be doing anything too complicated. And they learn very rapidly and very well. The question is, how do they manage to do this? How do they manage to implement such rapid learning? And as I've said already, it's through it's because they've got these active behaviors, innate behaviors that allow this rapid learning. And in particular, it seems like they're learning actions and not locations. I'm going to come on to what this means. And this means that the task they need to solve from a machine learning perspective is to learn for familiarity and not recognition. And again, I'm going to come on a bit more about what that means. So let's start with the first bit. So we think that in these animals that they use visual information to specify the action they should take and not location. And obviously for the purposes of this workshop, this is inherently an active approach, right? They're learning what they should do and not where they are. So again, a bit of background. We know that ants use visual information. And so there's many models which are based on this, which are collectively called the snapshot models. But since Tom Collett and Brian Cartwright came up with this model in the early 80s. The idea being that if I'm an ant and I'm trained to find food between these two cylinders, I learn what the world looks like from these cylinders, and I move later and move to make the world look more like my memory. And if I move until it looks like my memory, I'm back at the starting position, right? So if I move until the world looks the same as it did from here, then when I search, and we've got the search distribution here, I'll search in the correct place. And we know this because if we replace the cylinders in the test condition with one small and one large one, the ants will go and will search where the world looks the same. Okay, so they'll go close to the small one and away from the big one. And this is where the world appears to be the same as it did previously. So we know it's a very simple memory. So crucial thing here, you're remembering your view from the goal, not of the goal. And if you want to get back, you compare the view to your memories and you move to reduce the difference. And collectively, this is how all these kind of visual snapshot models work. In this case, when you're translating, we assume that the views are aligned. And by aligned, it means that the views, when I'm comparing the views, it's as if I'm always facing the same way. And this is because ants are sort of constrained to move in their faces. Constrained to move in the way that they're facing. So the views won't be aligned, but these were originally based on bees who can move, translate while maintaining a fixed orientation. We'll come to how this works. So in this case, the way one uses this, you get a stored view being an attractor to a location. And normally you can move back to that location from a region around the goal. And again, just to call back to the discussion, the reason this works, you can see that even very close to the goal, these arrows, this is a particular model, these arrows are not pointing directly at the goal, but it doesn't matter, right? So I think, again, probably in contrast to, as Mike One was saying, in contrast to our finely engineered robots, it wouldn't be very good for a self-driving car to be taking paths that were sort of 45 degrees wrong. But if you're in an open environment and you're an ant, it doesn't matter if you're 45 degrees wrong, you know, you're going to get back quite quickly to your goal with an iterative procedure. Okay, that's kind of an aside. Basically, what we have here is we've got a stored view being attracted to this location. So in this case, the view is specifying the location that I need to get back to. So this is kind of all fine. The problem with this is, firstly, that I need to be able to, I need my views to be aligned. Right now, how could I align the views? Well, if I remember views when I'm facing a certain direction, if I rotate on the spot and compare these scan views to my original goal view here, I get the minimum when I'm facing the same direction, right? So the point would be, for this sort of translation, for this snapshot model to work, what I'd have to do is, as the ants themselves do, I would, as I was moving along, before I did the matching, I'd rotate until I found the best matching direction, and then I can then move through this translated gradient in space and get back to where I am. So we have the behavior, we see this scanning behavior. This ant has been slowed down to 1/10 of its normal speed. So we know that the visual, they have these innate behaviors to enable a rotational matching. However, there's a more fundamental problem with using snapshots in this way. And the problem is that, as I said, you're constrained, the snapshot will get you back from a certain region around your goal, basically where you can see most of the objects that you could see from the goal. The problem is, so if you want to extend this, it was always assumed that you just chain these snapshots together. I'm going to home to this one, and I'm going to home to this one, then home to this one. And so we had this idea that routes were chains of snapshots. The problem was when we came to make this model, it didn't work very well. And it didn't work because the nearest two snapshots are telling me to do conflicting information. If I'm in between these two snapshots, one is telling me to go one way, and one is telling me to go the other way. And I get interference between these things, right? The problem is, it's not beyond, we made this model work, and we basically made it work by saying we had to be quite clever about saying, when did I get to this snapshot? Once I've gone past it, I stop using it. And you had to be quite clever about limiting the number of snapshots, specifying when to learn, where to learn, and I'd learn to identify the snapshot sequence, right? And so this is the idea, is that I'd have to do recognition. I have to learn where I am. And in classic teach and repeat, this is the same thing. I need to work out exactly where I am so I can work out what I should have done when I was previously there. And this implies learning the locations. We wanted to get away from this because it meant that we had to have quite a heavy bit of compute to learn this. So in our model, instead, if we go back to using a view instead of learning as a location, why don't we just learn the learn views as visual compasses? So in this idea, if I store the view when I'm facing the way I want to move, then comparing scan views to my memory means that as I rotate around and I find the best matching direction. Now, once I've found this direction, if I'm constrained to move in the way that I'm facing as an ant is, then I've learned the action I should take. So if I find the best matching direction, it is the direction I was moving. I'm now facing the way that I was moving when I was previously near this location. So then I just move forward. So in this way, I get rid of the whole location element, and I just learn what I should do. Now, without going into the details too much, now we get rid of the problem of interference, because now if I've got a chain of snapshots that are recording actions, or for any sort of sensible route that I take, all the actions around a certain area are all saying the same thing. So there's no interference between them. And I can just learn, I can match with any of the actions that I took from anywhere around here. If I'm around here, I can match any of these, right? So I now don't have to be very clever about when to learn. I can learn essentially continuously. I'll get many views to learn, but so I use these views instead of just learning them directly. I use them to train a neural network, and I can train this network for familiarity, which is just whether I've seen this thing before rather than which one I'm at. And so how does this help? Well, it helps because now what I need to do is I need to learn what I can now have is a behavior which structures the information so that all I need to do on my first route traversal is have information basically roughly in the direction I want to move again. And ants have this particular behavior called path integration. So when they first wander out in a new environment, they'll wander out randomly in a random direction. They'll keep they'll integrate their steps. So they've always got a vector which brings them back to the nest, roughly back to the nest. So once they found their food, they'll come back roughly directly to the nest here, right? So this behavior, path integration, means that on their first route traversal back, they're coming roughly directly back to the nest. And it means that the information that they're learning is implicitly is in the correct direction. Okay, so I won't label this point too much, but in training, the path integration, this innate behavior, means the views are implicitly in the correct orientation. So I just need to learn them as they appear. right? So this is what I meant about the innate behaviors structuring the information, right? The behavior means that I just need to learn, right? I don't need to do anything too clever with the learning. And then when I come back, when I want to recapitulate, what I do is I just rotate on the spot, find what seems to be the correct direction, and then just move forward. At each point, I scan and move forward, okay? And so I get from this what we call familiarity-based route navigation, and it's scaffolded by these two behaviors, path integration and scanning. In the interest of time, I'm going to skip this, but basically what we do is to learn the route, we just update a single layer neural network with the Informax rule. And when we're coming back, we sample the view. And if it's part of the route, I move in the direction I'm facing, okay? And we get views that are very similar, paths that are similar to the routes of ants. And we kind of think this is how they're working. So in here, I've got the red parts of the training routes and the black parts of recapitulations of the route. And they're kind of, if you squint and believe it, you get these kind of route corridors, which are reminiscent of the behavior we see in ants. And it's very robust. So if we can put it onto a small robot, so here we see, my videos are playing very slowly because I think my laptop's not working brilliantly. But in the top left, we see the training path and the robot wandering along. And in the other ones, we see recapitulations of the path. The crucial thing, sorry, my screen's going kind of horrible. But you can see people walk past and the robot just carries on. Okay, and it carries on because, why does this work? Why does it work so robustly? If we look at a view from the perspective of the robot in a different context, what you can see is that people appear tiny. You're going to see this person starting to walk along here. And whilst they're very salient for us, they're tiny in this panoramic viewpoint, right? All the information here is in the pattern of objects across the sky. And what you can see, what's most salient is when it returns, right? So changes in orientation are very, very salient. So taking an ant's eye view on this, we can see that the information can be learned very easily. Okay. And as I'm running out of time, I will skip about learning walks, but adding in a learning walk means we can do place search with the same mechanism. Okay, and at this point, I'm going to hand over to Namho, who's going to talk about how we can use these insights I'm going to stop sharing. So how we can use them in a lightweight app to work in for the blind and visually impaired.
Thank you, Andy. Should I share my screen or?
Yeah, do you want to share screen? Yeah.
Yeah. Sorry. Are you able to see?
It's just loading. Yeah. If you put it in presenter view, we'll grab it in a sec.
Oh.
Yeah, that's great.
Wait. Sorry about this. It's my computer is also quite lagging, but okay. I'll just skip through really quickly.
So this is a way of priming everybody's memories to remember everything I've said. You get it the slightly quick way and then the quicker way again.
Yeah, I wasn't able to load the presentation from my slide, but I think we're almost there. Okay. Go. Okay, cool. Thank you so much, Andy, and I apologize for this mishap. So yeah, I want to discuss the application-based implementation of the algorithm. And so just a brief overview of why vision is important. So when navigating through an environment, we all use our visions and we use different cues. But this is extremely difficult for the blind and visually impaired, where acquiring these different cues is not as straightforward as people who have sighted vision. And so, according to the WHO, it's estimated, that the total number of visually impaired people are about 285 million globally, where 39 million are blind and 246 million have low vision. And so, fortunately, there are a lot of different tools that exist to assist and augment the navigation tasks and for the navigation of daily tasks for these people. Like, for instance, you have the long cane, which does provide enough rich ground information, but it might induce embarrassing reaching behaviors when places are crowded. Pedestrians could trip, as well as there's no protection upwards. Another good solution would be guide dogs. However, when there's poor interplay between the actual user and the guide dog, it's quite expensive. And in countries even such as South Korea, guide dogs are not exactly widely accepted yet. And we move on to the sighted guide. A sighted guide refers to someone who's physically there for you and navigates and helps with everything right next to you, but it requires establishment of trust, and it's quite costly. And then we come to GPS solutions, where a lot of research has been conducted, but GPS mainly suffers indoors, and it only works within 30 feet, and it definitely has battery life constraints. So given these limitations, an idea that came would be, using the lightweight model of the ant navigation that we just discussed, and taking advantage of a smartphone, if we could deliver a more alternative solution that could address these limitations. And so before going into the application development, several interviews been conducted, and then due to the interest of time, I'll just skip to the demo of the actual application. So here we go. But essentially, here's a demo of the application. So there's a training sequence that occurs where the user would essentially step through the route. And so right now I'm stepping through, where I was standing towards the elevator route. Right now it's sped up by two times. So once the training sequence is done, you'll be able to save the route and extract the frames, which would be the views that are stored in memory. And then those views stored in memory will be now compared with the direct view that the user sees, as you can see on the screen right now. So we select the route path, and then as you can see on screen, I know there's a lot happening, but just to pause. You can see how on the bottom left, you have the view stored in memory, and then you have the difference that's been computing between the input frames that in real time versus the views in memory. And then on the right, you have a graph that represents the difference value between the two images in contrast. So when you have a high difference value, that means that the current view and the memory view aren't matching and not familiar, whereas when there's a low difference value, it means they're the most familiar and most matching. So it's also represented through a tonal pitch. So whenever there's a high tonal pitch in the application, the user can hear how the view is not matching, whereas if it's very low, then they know that they're the right path walking towards to. Yeah. So this is the application, and you'll be able to test it if you want to. And yeah, thank you so much.